I'll start with the first trend, and that's Moore's law. Again, I assume most of you are familiar with Moore's law. Gordon Moore, about more than 40 years ago, said that the number of transistors and resistors we are going to be able to push into a silicon chip is going to increase, is going to double every 24 months. Actually, later it was fine-tuned to double every 18 months, even faster than what he predicted first. And the interesting thing is that it has held for more than 40 years. And people are talking about Moore's law dying. Moore's law didn't die yet. We still have all kinds of predictions. But if you look at the number of transistors that we push today into the die, it's doubled than what we did about 18 months ago. And we still predict that it is going to stay alive for at least a few years from today. But, and here is a very important thing, Moore's law is talking about transistors. And I assume that you guys don't care much about the transistors that are being pushed into a silicon chip, into your processor. What you care about is the performance. What you care about is flops, being able to do calculations, multiply matrices, or solve your problem. And here's the deal. While transistor number is still growing, the performance you're getting is flattening. Which one is the performance? This one. The performance numbers are not growing anymore. And there are multiple reasons for that. One of them is that if you look at the first few years, like 20 or 30 years, it's not just the performance that doubled, also the power consumption of the chip doubled. And we have arrived at a limit that we can no longer grow. We cannot consume more power into a single chip for multiple reasons. I'm not going to go in there today. So we are limited with power. As a result, we are limited with the frequency. We already know that the frequency of the chips is not growing anymore for a few years now. And bottom line is that a single thread performance of a CPU is not growing. So we started pushing more and more cores into a CPU, but it's not growing fast enough. So what's happening is that, yes, Moore's law is alive. We can still push more transistors, but the performance we can get out of the CPU is not growing fast enough. We know that we need faster computers, and a CPU is not getting fast enough. So we see a very interesting trend. One of them is adding accelerators. Accelerators are using different architecture. And by adding more and more floating point engines, not doing faster floating point, but by doing more parallelism, we can actually somehow cover the gap. We get more performance using accelerators, and this is, again, you've heard about accelerated computing yesterday. This is one part of solving the problem, and that is using different accelerators in the system. It's no longer a CPU-centric system. The future systems will have different accelerators. GPU is one example. It's not as flexible as a CPU. There are many things that the GPU cannot solve. But the problems that the GPU is capable of solving, the GPU is doing that much faster than a CPU. And we will see accelerators for security and for different other tasks. So the system is getting more complicated with CPUs that are very flexible, and other types of accelerators, either GPU-like, which is still a very programmable kind of processing engine, and all the way to ASIC, a very mission-specific accelerators. And we see all kinds of those solutions today. The second trend I want to talk about is the exponential data growth. Again, you've heard about it yesterday. And probably most of you know that. You have the data. And the data that you hold is growing, and the problem is how to get information, how to get meaningful things out of the data. And data is growing everywhere. 90% of the data that exists today has been created in the past 2 years. There is a huge amount of data being generated from, in about 15 years, the amount of data that we have had grown 300 times. We generate a lot of data, we collect a lot of data, we make money out of data. If you look at the past 20 years, the 10 companies with the highest market capacity, in 1998, most of those companies were either oil, energy companies, or banking. Also, we had technology like Intel and IBM and Coca-Cola, but look at the list. Oil is a very important asset in 98. And then if you go to 2009, still, oil is a very important asset. We still have technology companies and we have pharmacy, but still oil is very important. And if you look at 2019, many of those companies make money out of processing data, getting good information, important information out of data. Google, Facebook, what they have is data. They collect data from everything that we do and make money out of it, make a lot of money out of it. They're a very important part of the economy, and you can see many companies like that that move to make money out of data, and oil is just the last one out of the 10. Only one company in the top 10 is oil company. This is just another example. Now that we are going to autonomous cars, those cars have many sensors. Sensors collect a lot of data, generate a lot of data, and again, we want to do meaningful things out of this data. Think about it. Today, we have just a few of those cars. Once each and every car on the road will collect this amount of data, again, we will generate huge amount of data every day just by driving. I'm coming from Tel Aviv. I arrived yesterday, flying out today, back to Tel Aviv. It's about 12 hours of flight. This is the example in the right is for Whitney Houston airplane engine. This is not the one that I used to arrive here. I actually arrived in a Boeing that is using a General Electric engine. But it's about the same. They both have a huge amount of sensors monitoring the engine during the flight, generating terabytes of data for each engine, for each flight. Again, this is just an example. We will have sensors everywhere. We will collect a huge amount of data. We want to be able to monitor the data, to analyze the data, to make meaningful decisions based on the data. With the engine, we want to increase the safety of the flights. We want to make them greener. There are many things we can do with this data. And the last one, actually this is not the last, this is the third trend that you have already heard about. If you want to use deep learning, if you want to use neural networks, we use more and more complicated neural networks to have more accurate decisions. And I'll get back to it later today. And the last trend, this one is the last trend, it's the pizza trend. We eat a lot of pizza. It has nothing to do with your computers. We eat a lot of pizzas. For the Super Bowl Sunday, Americans will buy 12.5 million pizzas on Sunday, one Sunday. We'll get back to pizza. There is a reason I talked about pizza, but for now it has nothing to do with the trends. So with the growth of, oops, sorry about that, we generate more data. We use very complicated neural networks to analyze the data. And the CPUs or the processing engines are not providing enough compute power, are not going to be fast enough in the next few years. And there is only one solution today. And that's probably the most important solution that I'm going to talk about in the next half of this talk. And that's connecting a very large amount of processing engines. If you want to solve today's problem, if you want to solve tomorrow's problem, if you want to analyze the huge amount of data, there is no single processing engine that allows you to do that. The only way to do that today is by connecting a very large amount of processing engines into a single computer. So a computer today is not one CPU, it's not one GPU, it's not 8 CPUs and 16 GPUs. A computer today and tomorrow's computer is thousands of processing engines. It's a collection of different architectures of processing engines, being CPUs, GPUs, accelerators. And the only way to make this CPU work, to make it efficient enough, to make all those processing engines work together, is by connecting them with a very fast and very efficient interconnect. In this slide, it says faster interconnect. And what I'm going to try and convince you today is that fast interconnect is not enough. Fast is good. Yes, you need a fast interconnect. But being fast is not good enough. I had to brag, OK? 3 of the top 500, the fastest supercomputers today are using our technology, are using the technologies that I'm going to present today. I'm going to show you how we believe and how we solve today and plan to solve in the future the mission of connecting different processing engine in a very efficient way. Number one is the Summit supercomputer, about 27,000 NVIDIA GPUs, Volta GPUs, working as a single supercomputer to solve scientific problems, to solve AI type of problems. Number 2 is Sierra in Lawrence Livermore, and number 3 is a Chinese system in a supercomputing center in Wuxi, east of China, for those of you who don't know. All of those supercomputers are built upon connecting a very large amount of processing engines with a very fast and efficient interconnect. Talking about AI, if you look at the latest breakthroughs, the new records, with training, most of them are focused on image processing. This is where we excel the most. All of them are using systems accelerated by the Mellanox interconnect. If you look at the different software frameworks to run AI, to run deep learning, all of them are using Mellanox technologies, supporting the RDMA and acceleration technologies that I'm going to talk about today. And this is probably the most important slide for today. For me, if you understand this slide and remember that and go out of here with this understanding, I'm OK. This one and the pizza. These are the two important parts of this talk. If you look at the old way of doing clusters, connecting CPUs and GPUs and connecting to storage, everything was around the CPU. The CPU is the most important part of the system, is the center of the system. And if you want to process data, you need to move the data into the CPU memory, then into the CPU registers, and then the CPU can actually process the data. This is the old way. It's true for CPUs, for GPUs, for any processing engine. If you want to process data, you need to move the data from where it's stored or where it's generated all the way to the processing engine, the CPU, GPU, ALU, the floating point engine that actually crunch data. The problem is that it's not good enough today. Since both CPUs and GPUs, they are fast, they can process a huge amount of data at a very short time, it's almost impossible to get all the data in there fast enough. So what we are trying to show is that you need to rethink the cluster or the system architecture, and instead of having a CPU-centric or processing engine-centric architecture, we need a new architecture which is now data-centric. Data is everything. You care about the data. You want to process the data wherever it is. If you can process it where it's being generated, that's the best thing to do. Our part of it is looking at the networking and making the network not just wires that move data between one processing engine and another, but as an opportunity to do things with the data. And here is the pizza. I told you I'll be back to the pizza. This is an example. Let's say I really like pizza and I want to order pizza. I don't make my own pizza, unfortunately. And there is a process, a very familiar process. You call the pizza place, and they start making the dough, put the tomato sauce and whatever you want on your pizza, put it into the oven, and now they wait. It's about 7 minutes. It depends on the pizza and the oven, but it's a few minutes. Once ready, they take it out, pack it, and send it to you with the pizza driver. It takes 25, 20 minutes. It depends on how far you live from the pizza place. But think about that. Let's say that you could have this kind of pizza truck. So, okay, you will call the pizza place, they make the dough, puts everything that you need, put it into the oven and start going. Now, while the pizza is being delivered, while the pizza is being moved, you actually do things with the pizza. You bake it. It will get faster to you, it will get warmer, fresh. We look at the network as a similar thing. You have the data going through the network to the processing engine. There are things you can do while data is being moved to the processing engine, just like the pizza. So in the old way, you had to move data to your processing engine to start processing it. And for today, I'll use a single example. I'll take an example of distributed deep learning. Let's say you have a neural network and a lot of data, and you want to train your neural network to do something. Let's take the easiest example. You want your neural network to be able to do image recognition, to say if there is a cat, a dog, or a pizza in your picture. The way to distribute this kind of problem, the most common way, is to have multiple copies of your neural network, one running on each processing engine, and train those on a portion of your data set. You have a huge amount of data. Each processing engine now only sees a smaller amount of data and do training. But as a result, you want a single neural network that is trained by all the pictures. This is the most accurate and best way to train. So what's happening is that after each iteration, you have to synchronize the neural networks between all the processing engines. This is done in a common operation, and you'll have to trust me. Either you already know that, or you'll have to trust me. What you have to do is calculate an average on a long vectors between all the processing engines. Each one of them is calculating the small fixes to the neural network, and now you have to average those and apply to the actual neural network. Averaging the vectors, either you send them to one CPU, and the CPU is now processing the average and sending back the result, which is a very inefficient way to do it. There are actually better ways. I won't get in there today. You could do that in the network. If you are going to send all the data from each one of the processing engines to the network anyway, because this is the only way to get to your CPU, let the network do the averaging. And again, I'll get back to it later today. So what we believe the future of the systems will look like is a collection of many different type of processing engines, CPUs, GPUs, accelerators for security, ASICs for specific missions, FPGAs. And they are all going to be connected with a very efficient and fast interconnect. And I'm saying efficient first because now I want my interconnect not only to move data as fast as possible. I want it to do more than that. And we already have different processing engines implemented into the network. We will not be able to go through all of those technologies, but we will go through a few of those technologies. But before that, yes, you need faster interconnect. You actually need high bandwidths. You need to be able to move a lot of data between the processing engine. What I'm trying to show here, this is based on Sylvain's presentation in the last GTC in San Jose on Merge by NVIDIA. He was talking about accelerating AI with DG Xbox, and this is an example of the internal bandwidth within a server. So if you look at a single server, either you have two Intel CPU sockets connected with the Intel coherency bus, the QPI, with somewhat low bandwidth, somewhere between 6 and 9. If you go to a PCI Express switch connecting those two sockets, you get higher bandwidths. If you go to NVLink, just like in DGX1, you get much higher bandwidths, and if you go to DGX2, you actually have NVLink switch connecting 16 GPUs with very high bandwidths. And this is all within a single server, but we already talked about the fact that a single server is not going to be enough. You will need to scale way beyond a single server. Hundreds or thousands of those servers will need to connect in a very efficient way. So you need to match these bandwidths with external bandwidths, and here is what Sylvain present as a recommendation. If you're using QPI, don't waste too much money on Interconnect, because even within the server, you don't get enough bandwidth. But if you are to use DGX-like boxes with very high speed connectivity between the GPUs within the server, you must match that with external bandwidths. DGX1 have 4 network adapters of 100 gigabit per second each. That's a total of 400 gigabit per second. DGX2 has actually 8 of those adapters, providing 800 gigabit per second. And yes, this is a very easy for me to present someone else's slide, but this is a benchmark that we have measured. What we did is connect 32 GPUs. It was, I think, 4 GPUs per box, with the Mellanox Interconnect, and train a VGG16 neural network on ImageNet. Again, we took neural network, trained it to recognize pictures, and what we did in this test is to configure the network to either use 10 gigabit per second, 25 gigabit per second, or 100 gigabit per second. Exactly the same system, just a configuration to the network adapter to either use the full speed of 100 gigabit per second or limit the speed to a reduced speed. And you can see that by increasing the speed, you actually get much faster processing of images. What you see here is the number of images per second the neural network can process. The more images you can process per second, the faster you can train the network. OK, so we agree that speed is important, but that's not enough. The second thing is the protocol that you are using. Everyone here probably know TCP, right? Anyone who don't know TCP? That's easy, no one will raise a hand, yeah. So TCP is a very common and very nice protocol to move data. Each server that you buy and install and put your, let's say, Linux operating system will have support for TCP. The Linux software actually implements the TCP stack. So what happens is that in order to move data in and out of the server, you need your TCP code that is a part of your operating system to run and process the packets going in and out into, for the server. For slow networking 10 years ago, that was good enough. For very fast networks, the CPU is not fast enough and not efficient enough in processing those packets. And what we provide for the past 20 years is a new protocol. Well, it's not new anymore. It's a way more efficient protocol called RDMA, Remote Memory Access, Direct Memory Access. And the idea is that I want to provide data for a GPU to process it. I don't want any CPU code to touch this data. There is no reason to go and process those packets. I want the networking infrastructure to handle networking, and the CPU and GPU to process data. I don't want the CPU to move data. That's an inefficient usage of CPU engines. And again, we compared RDMA to TCP. What you see here is the speed up. If you have a single GPU, you get some processing power. If you have 32 GPUs, ideally, you would like to have 32 times the processing power. Unfortunately, that's not possible. You do pay some overheads to move data between the GPUs to do the synchronization. You want this overhead to be minimized. If you look at TCP, what you get out of your 32 GPUs is about 20x acceleration compared to a single GPU. You actually paid for 32 and only get about 20. If you do RDMA, you get to about 31x acceleration. So again, you don't get 32 times processing power than a single GPU, but you are almost there. What you have here is the yellow line is the ideal theoretical acceleration. So you are actually getting very close to the ideal acceleration. Next technology you need is now we moved a lot of processing from the CPU to the GPU. But again, as we said, systems were built centered at the CPU. So data movement, the CPU had to deal with data movement. If you want to process data, the CPU needs to get the data into the CPU memory and now move it to the GPU to allow it to process. And if you want to move it to another GPU, you had to copy the memory from the GPU memory to the CPU memory, send it to the remote CPU, copy it to the remote GPU, and only then the GPU can start processing. During that time, you have GPUs that are waiting for data. The worst thing to do is wait for data. You want GPUs to process data. This is what they are good at. And now what we do together with NVIDIA was to develop this GPU direct technology that allows GPU to communicate through the network without going through the CPU. We move the CPU from the data path. It allows us very high bandwidths, much lower latency, and way more efficient ways to move data. So we talked about moving data. We said we needed to do it fast, very good protocol, bypass the CPU. Is that enough? No. Again, by GPU Direct, we accelerate and get more performance. But this is probably the most interesting technology that I wanted to talk about today. It's called SHARP, Scalable Hierarchical Aggregation Protocol. This is the pizza truck. This is where we actually process data while it traverses the network. You have your hosts, servers, GPUs, CPUs, whatever processing engines connected to a network, switching network. You do deep learning training with gradient descent and very sophisticated algorithms, and now you have to calculate average. What you do is each of those processing engine is sending the data to the switch. The switch is doing the averaging, sending the averaged data up the network, and then the aggregated result, the average, is being sent back directly to the processing engines, to the GPUs. So now instead of moving a lot of data to one GPU or then calculating the average and sending the result, or doing some more sophisticated algorithms, distributed algorithms where you send the data back and forth multiple times, you just send the data to the network and get a result. If you look at it, what we did was actually add processing engines, floating point engines, to the switches. And we don't claim that we know how to better implement processing engines. It's not that we know something that Intel or NVIDIA don't know how to do. I mean, floating point calculation is not that hard to do. Usually the problem is, how do I get the data into the processing engine? So instead of asking this question, how do I get the data into the processing engine, we know that the data crosses the switches. We put the processing engine where the data is. And by doing that, we get a way more efficient way to process the data. Not because we have better processing engines, just because we put them in the right place. If you look at how much time it takes to average those vectors, usually the more nodes that you have, the more GPUs that you put into your cluster, it will take longer. We compared software solution based on CPUs or GPUs. You see that when we put more GPUs or put more nodes, what happens is that the amount of time it takes to average the vectors from all those nodes is higher. When you use the hardware mechanism, when you use the switch mechanism to actually calculate the average, there is a flat latency. So if you have 2 nodes, if you only are going to use like 2 servers, software is good enough. We don't care about those kind of problems. But if your problem is big enough and requires more power and more GPUs, what happens is that the more GPUs you put into the system, the more time you spend on waiting for averaging the data. So you have many GPUs, many processing engines waiting for data. The more processing engine, the more time they just waste on waiting for data. This is on a larger number of processing of servers, 1,500 nodes, again showing flat latency with in-network processing compared to software processing. Probably you don't care about how much time it takes to average some vector. What you care about is how much time it takes me to train a network or to run some processing, some application. This is one example for high-performance computing type of application, scientific application. Again, with providing 18% more processing power, total processing power to your application. As we said, when you go to deep learning, what happens is that if you look at the way TensorFlow, for example, used to implement this averaging is by running processes called parameter servers and doing the calculation in those processes. What happens is that we offload those processes. You don't need those processes anymore, and the switch is doing that for you. With this technique, what happens is that the more GPU you have, the higher the gap between just doing it the old way and doing it in network. Unfortunately, the largest GPU cluster I had when doing those measurements had 22 GPUs. You can see that for 22 GPUs, the gap is 16%. You can see that for 16 GPUs, the gap is 11%. For thousands of GPUs, the gap is going to be much higher. And at some point, the problem is that if you do not use this kind of technology, you get to the point where adding more GPUs, what happens is that now you wait more time for the averaging. What happens is that you add GPUs but don't gain any performance. So with the old technologies, the maximum compute power you can build is limited. It's not limited by power or money. You can buy more GPUs, it will not buy you more performance into your total system. And the reason is that the more GPUs, the higher the overhead you pay for the parallelism between the GPUs and communicating between the GPUs. And the only way to break this limit is by using new architectures, doing things in a more efficient way. It's not enough to be faster network. You need to actually move some of the processing to where the data is and not always move the data to where the processing is. And now the last question is, okay, so I have this technology, which is great. How do I use it? I have my application. I bought, let's say that I have the DGX boxes connected with Mellanox InfiniBand switches. I'm not going to rewrite my application. I want to either download TensorFlow or Caffe or PyTorch and run some neural network training. And then the good answer is that today NVIDIA provides a communication library that is being used by all those frameworks called NCCL, NVIDIA Collective Communication Library. It's being supported by all those frameworks, and it implements the communication required, for example, for averaging the gradients, averaging those long vectors. This is probably a not very interesting, but the history of those, of nickel, it started with a single server trying to optimize the communication on top of NVLink. Then NVIDIA started supporting communication between multiple servers. Again, a single server is nice, it's just not enough. For many of the large problems, a single server is not enough. So Nickel 2.0 supports connectivity between servers, supports RDMA, and starting at 2.4, it actually supports Mellanox in-network computing. So if you have the hardware and you download TensorFlow with the latest Nickel library, you get the acceleration. Let me skip a few details. You get full support for the sharp acceleration and RDMA and GPU Direct and all the different technologies we've talked about today. And you get the gain of performance. And this is the most important part. Yes, we talked about technology. What you care about is not, I'm going back to Moore's law. You don't care about the number of transistors in your CPU. You care about how fast can I process the huge amount of data that I'm generating today? Or how deep can I analyze the data that I'm going to generate in the future? In the coming 2 years, I'm going to generate a huge amount of data. How much information can I get out of it? And to get a lot of information, you need very complicated neural networks. You need a processing engine that can train this neural network with the huge amount of data, and only then you can actually get the information or the decisions you want to make based on this data.